Welcome to my channel once again. This is Tisha Tari. In our last videos, we spoke about we are able to establish that products are liberated at each of the electrode. So the quantity of this product that are liberated at each of the electrode is determined by three factors. So one of them I'm going to talk about is the magnitude of the steady current, the magnitude of the steady current. The magnitude of steady current. Two, we said the rate of flow. The rate of flow of this steady current. Three, we said the ionic charge. The ionic charge of the liberated element. So in this, we said these three factors influence the quantity of the product that is liberated at each of the electrode. This aspect of electrolysis is studied by a man known as Faraday, and he gave us two laws to explain this concept. So the first law of electrolysis is known as Faraday's first law of electrolysis. So the first law, I'm going to explain the first law of electrolysis. It talks about the mass of an element when the mass of an element is directly proportional to the quantity of current. Say during an electrolysis, the mass m of an element liberated at each of the electrode is directly proportional to the quantity of current passing through them. We said m, the mass of m of an element discharged during an electrolysis, directly proportional to the quantity of current passing through them. So we're going to take this one to be equation 1. For us to change the proportional sign, we said m is equal to, we're going to introduce a constant known as electrochemical equivalent, Q. Let's take this to be equation 2. By so doing, we said this where m is the electrochemical equivalent, and it is given as a constant in this aspect. We said Q is the what? Quantity of current. In coulombs, always given in coulombs, or it is also written as capital C, represented by capital C. So in all this, we say for us to identify or define quantity of current, we must know the current and the time it took for us for the flow of this current. We said Q is equals to, we must know the current and the time taken. We said this is the ampere, while this is given in seconds. So if it is given in minutes, it must be converted to seconds. So this brings us to the equation. Let's take this to be equation 3. So let's replace this Q with IT. We said by so doing, you're going to have the first law of electricity gave all this concept. M is equals to E I T, where it is electrochemical equivalent. I is the ampere. T is the what? Is the seconds. So after this, Faraday gave us this the minimum energy or the minimum electricity needed to liberate each of these elements by a constant known as Faraday constant. We said for the quantity of current needed to liberate 1 mole of any single charge, a very good example of ions that contain single charge. We'll talk about the group 1 element. Let's use sodium. So sodium, we acquire 1 electron to give metallic sodium. For instance, we said the quantity of current needed to liberate this 1 mole of this sodium is given with a constant approximately 96500 coulombs. So for 1 electron, we need the quantity of this current. If for elements that have two electrons, like copper 2+, like a magnesium 2+, we say it needs 2 times 96500 coulomb to liberate this this 1 mole of these substances. So for trivalent element like aluminum, it will need 3 times 96500 coulombs. So by so doing, each of these charge influences the quantity of current that will be needed to liberate 1 mole of these substances. Please take note of each of them. So know when a given ion is giving out 1 electron, 2 electron, 3 electrons, so that we can be able to manipulate this in our calculation in electrolysis. So this takes us to second laws of electrolysis. Second laws of electrolysis. So the second law of electrolysis is different from this first law. Second law. So the second law gave us a better idea that if the same current is passed through different electrolyte, we said the mass m of the element is directly proportional to the chemical equivalent. We said if the same quantity of current, when you see in any calculation problem that the same quantity of current is used, just know that you're talking about second law of electrolysis. So if the same quantity of electricity is passed through different electrolyte, we said mass m is directly proportional to the chemical equivalent. So let's remove this proportionality. You're going to have equal to, let's introduce ZE. So we talk about this is chemical equivalent, or the weight, chemical equivalent. So chemical equivalent is given, let's take this as equation 1. Chemical equivalent E is given as mass of the substance all over number of electron involved in the reaction. That is to say, for us to know the chemical equivalent of silver, for instance, silver, the mass of silver, 1 mass of silver is 108 gram divided by what? By 1. So the chemical equivalent of silver is 108. So by so doing, the chemical equivalent of, let's use copper for instance. Copper will give us 63.5 divided by 2. It's going to give us 31.5. By so doing, with this explanation, we said if the same quantity of current is passed through these 2 ions, more of these silver ions will be liberated at each of the electrode. More of these will be liberated. We have 108 of these. We have 31.5 of these. So for us to know the chemical equivalent, we must know the mass of the substance and the number of electrons involved. So for if two ions are present in the reaction, for instance, are liberated at both ends, we said we're going to introduce an equation known as M1 to represent one of the ion. We're going to use M2 to represent one of the ion. We're going to use a chemical equivalent of 1 to what? Chemical equivalent of 2. This equation will be known. We'll use this equation to solve problem on second law of electrolysis by Faraday. So this is the end of the lesson. Please try to make up your mind and study this aspect of electrolysis. And we're going to use each of these equations to solve calculation problem on electrolysis. So in our next video, we're going to bring some questions that will reflect the use of this equation. Thank you very much.